Hello everyone, I'm Zhou Bingkai, come from Shenyang University of Technology. I'm glad to introduce our work on AI algorithm of military chase. We know that neural networks have been successful in many problems of giving AI, but many of these AI programs are based on reinforcement learning and end-to-end designs. Many times, we don't have enough computing resource and energy to support our use these models. But if we use traditional AI algorithm based on game research, has to pay a lot of manual adjustment. Because the situation evaluation function must design manually. So, how to combine the advantages of these two methods is a problem worth considering. In this paper, we study a method combining neural network and game research, and take military chase as an exam. The architecture of the whole model is shown in the figure. You can see that we use the traditional probability means to reasoning on the enemy's pieces, because in military chase, we don't know that exact type of enemy pieces, but we must have an estimate of the result to game research. Then, according to the knowledge of military chase, we extract the features of the current situation. These features need to be able to reflect the strength competition between the enemy and us to a certain extent, and provide the basis for the next decision. With these two information, we can use neural network to estimate the winning rate of the current situation and give a score. This is the value network shown in the figure. Value network is used to evaluate the situation. Then, as long as the evaluation function of the last layer node in the game research is replaced by value network, in this way the combination of the two is completed. These are our architecture of our model. I'll introduce these modules one by one. The first is dark chase reasoning. We use probability matrix to describe the probability distribution of all pieces of the enemy. The probability matrix is shown in the figure. We give each enemy piece a number, and the column of the probability matrix corresponds to each piece of enemy. The row is all the types of the chase pieces. When initializing the probability matrix, difficult positions on the chessboard have difficult pair probabilities. For the pieces in the base camp, in the last rows, and not in the base camp, and not in the last rows, the pair distribution is shown in the page formula respectively. As the chase game goes on, we will get credible information about the enemy's chase type from the enemy's layout, chase playing, and the fighting results of both sides pieces. This information is used to update the probability matrix. There are three main types of information. At first is layout rows. For example, bombs can't be placed in the first row, mines can only be placed in the last two rows, and military flags can only be placed in the base camp. Secondly, movement rules. For example, the engineer can return around on the highway. It must not be a mine that can move. At last is fighting result. If we are defeated, the enemy's chase strength is greater than ours. If we are victorious, the enemy's chase strength is less than ours. If both sides are exhausted, the enemy's chase strength is equal to ours. Our enemy's is above. On top of that, there are rules that only engineer who can defeat our mine. After obtaining the information, we need update probability. The core formula of update probability is obtained by Bayes' theorem. It's in the page. After introduce the reasoning part, let's look at the feature extraction part. This part is very important for the situation evaluation of neural network. The situation features of military chase can be roughly divided into four categories. The score can be divided into total value and extra value. Total value describes the correct strength condition between the enemy and our chess pieces. Extra value describes the impact of the situation details in terms of position, moving ability, and instruction. When the situation evaluation function is designed manually, the four features are weighted and summed to get the final situation score. And in the model of this paper, these four scores are input into neural network as independent features. Then let's consider the value network part. First of all, let me introduce input of the network. First, the chessboard and the probability matrix must be inputted into the network. In addition, we also need a coordinate mapping table. That is a matrix describing which position on the chessboard is each row of the probability matrix corresponds to. In theory, neural network can make a correct judgment by using this information, but this kind of fitting is difficult. Therefore, it's necessary to input the situation features extracted to assist the judgment. Then let's talk about the architecture of the network. First of all, we need to connect the chessboard, probability matrix, and coordinate mapping table into a matrix before actually input the neural network calculation. In this way, the convolution layer can be used to deal with it as a whole. The convolution part only deals with this matrix and doesn't deal with the extracted situation features. The architecture of convolution part refers to AlphaGonku, that is a small Go-bound neural network model. This model is a militarized and effective implementation of AlphaZero. We refer to it because its board size is similar to military chess. At the end of convolution part, we get a smaller feature map. Then we find it and connect it with the extracted features to form a one-dimensional tensor, which is sent to full conditional layer. Because the number of features is not large, so a few full conditional layers are used to process the results. The result is a probability value representing the winner rate, which is output by the sigmoid node. Okay, the value network described in the previous section is a function of situation to winning rate. Therefore, the training is carried out by marking the winning and losing situations. We use an automate method to obtain training data and conduct incremental training repeatedly. The untrained model matches with our other AI programs we've collected. Every match will automatically save the chess manual and mark the winner or loser. At the end of matches, the overall winning rate will be counted, and then the chess manual will be divided into situations, and our situations will be marked according to the winner or losing of the match. In this way, we can get the data that can be used for training. Every time new data is added to the original data for training, is to avoid repeat the model effect caused by expensive situations. Each training is based on the model with the highest winning rate. When the winning rate reached a threshold, random self-play training is started. Randomly selected opponents will be used for each match. Using this kind of incremental training can enhance the model's ability to deal with difficult types of opponents. That's all I want to say. Thank you.